machines.
Thank you. And I would like to thank the organizers for giving this opportunity to speak here. So I come from an electrical engineering background, and I also come from the transport background, which is basically, as the devices get shorter in size, we have this whole quantum transport, where basically, you have these source and drain reservoirs that's communicating with the channel, and the current sort of flows because of a voltage that is applied between the source and drain. But today, which is why it's an open system, which is why sort of here, but what we'd like to sort of draw the attention is the fact that you can also connect with some sort of demons. I would like to emphasize that word. I mean, it's not in a negative connotation, so I will just try to tell you. So for example, you can sort of drive the channel currents using this out of equilibrium demons. Examples of out of equilibrium demons are, for example, when the phonon bath goes out of equilibrium. For example, in suspended carbon nanotubes, the phonons can sort of go out of equilibrium. Then you can also have a nuclear spin bath, which can be polarized in some weird fashion, and then it can drive the current. So I would like to first introduce this, the phonon bath. Then I will slowly graduate towards this, how the hyperfine interaction can be thought of as a daemon or an information source, and how it can sort of run a heat engine. And then finally, in the strong coupling limit with the spins, you can also get some funny entanglement scenario. So, a little bit about our background. As I keep saying, the devices got shorter and shorter, and therefore we are in this 14 or 20 nanometer where everything is quantum. And that's the reason why we use this quantum transport theory, which basically has some semblance with this Landauer formalism, which says that the current really flows when I put a voltage, and those states that are sandwiched between the two chemical potentials are the ones that contribute to the current. So basically, the reason we have open systems is our whole device is sort of divided into two parts. One is the channel, which is what is conducting current, which is what got really short, as the nanotechnology comes up. And then you have the source and drain electrodes that are sort of the reservoirs that give the current. And so basically, if I put a voltage, I sort of maintain a different chemical potential between the left and right, and electrons hop in if there are states available between mu1 and mu2, and therefore you get a conventional current that's sort of opposite of the electron flow. And the battery's job is to maintain that chemical potential gradient, right? So some of the areas we work on is basically, charge-based logic, spin-based logic, also work on nanoscale transfer. But today's talk is more about this whole single spin manipulation and things like that. So there are two favorite methods to do transport. One is this famous Schwinger-Keldysh non-equilibrium Green's function, which is actually very popular in the electrical engineering milieu right now. And people have, there are a lot of multi-billion-dollar, solvers that use this Keldysh non-equilibrium Green's function. This is actually valid in the self-consistent field limit, or a little bit beyond that in the Kondo limit and things like that. But the important point is that it works when the coupling to the contacts, which is actually called as level broadening. Level broadening is significant compared to the charging energy. Now we have this other method, which is what I will be talking today about, is this, the Fock space way of looking at transport, which is basically when you neglect coherences, it is simply a master equation sort of approach. And when you do have coherences, it sort of becomes a Lindblad style of equation. So I'd like briefly introduce you to the Fock space picture, because that's what I would like to, my rest of the talk is about this. So simplest case, when you have an energy level sandwich between the chemical potentials, electron hops in and hops out and the current flows. Now that can be viewed as up transition and down transition in Fock space, where the Fock space of a one energy level is just a 0 and a 1, it's like binary. So you either have occupancy or you remove it. So there is a rate at which it goes up and comes down, like optical transitions. Now the important thing is, where this thing becomes slightly non-trivial, is when you have charging with this single level. For example, you have upspin and downspin degenerate levels, but there is this U, charging energy. Now because of that, in Fock space, you have 4 levels, that is basically not occupied, upspin, downspin, and double occupied state. So these are the 4 Fock space levels that characterize the single particle level that you sort of know very well. Okay? So the way we do transport is, this is the generic picture that, levels between mu1 and mu2 conduct. For us, it is basically transitions between an n particle state and an n plus 1 particle state. We calculate these non-equilibrium probabilities. The important point is that this method scales as 2 to the power n instead of just n cross n. And therefore, it's not very, computationally very feasible to do all this electronic structure and chemistry, right? So in this picture, there are these transition energies which are the difference between the many body states, which have, for example, En plus 1 minus En gives you this particular transition energy where I can add an electron. So if you want to view it in the single particle picture, you'll have to consider those transition energies. So I would like to now introduce this quantum dot heat engines now. So we'll move to the second part. As I told you, one way to drive currents through a device is to put a voltage. The other is you can put a temperature gradient also, which is basically the thermoelectric effect discovered by Seebeck and Peltier in 1800s. The reason why it's not yet so popular is because of the efficiencies and other things like that. So basically, when you put a temperature gradient, you can also drive a current, and that's basically, it acts like a battery, right? So let me explain you what happens from an electrical engineering perspective. So there are all these thermodynamic interpretations of the thermoelectric effect, which is okay. But simple thing, what happens is that when I don't put a temperature gradient, what we guys plot is the current voltage characteristics, that is the I versus V curve. And when there's no temperature gradient, it passes through the origin, because you would not expect a device to, generate power when there is no, voltage. But when you put a temperature gradient, there is this curve which offsets up or down. So that gives rise to this region where the power is positive. In electrical engineering terminology, it's negative power, so it depends on how you define power. So this is the region where useful power can be drawn from the device. And this is basically called the short circuit current, and this is the open circuit voltage where the current becomes zero. And so this is called the Seebeck voltage and things like that. And what really drives this current, or what really gives you this counterintuitive flow, for example, mu1 and mu2, when I put a temperature gradient, you actually have mu2 higher than mu1, but still the current, electrons flow this way. It's kind of counterintuitive, and that's why you draw power from the device. And that really happens because of this, free energy condition, where epsilon minus mu1 by T1 is greater than whatever is by T2 on the right side. So this is the basic idea of thermoelectric. So let me just talk about the single resonance state, epsilon. So it's a very famous story that a single quantum dot heat engine can reach the Carnot efficiency. It's a very famous thing that was derived by Mahan and Sofo, and it caused a lot of furor in the thermoelectrics community. So let me just explain you how this happens. For example, so what we plot is the power versus voltage curve. So as I told you, there are these 2 points, the open circuit voltage and the open circuit current and the closed circuit voltage. So basically the power is positive in that region, which is basically between the short circuit current and the open circuit voltage, and both points have zero power. So in between there is this power which you can draw from the device. And this, for example, if for 2 different temperature gradients, you see a lot more, compared to the first one. Now, when you plot the efficiency, you actually can show with a simple argument that at the open circuit voltage, you actually reach the Carnot efficiency in this sort of an engine. Now, there is a catch, of course. Carnot efficiency sounds great and stuff like that, but you don't draw any useful power because the power is zero, right? Because the current is zero, and Carnot is basically the quasi-static limit. So unfortunately, there is this trade-off between the efficiency and power, which we have in these heat engines. For example, you have the maximum power when the efficiency is not the maximum. So that's called the power efficiency trade-off in heat engines. Yeah. So I'll talk about this now. What I showed you right now was a heat engine without this phonon degrees of freedom. Now I'll just talk about a situation where the phonons are also there and the dot interacts with a single phonon mode. And that phonon mode can go out of equilibrium like suspended carbon nanotubes. It's not science fiction. There are lots of experiments that kind of show this non-equilibrium phonon signatures. So this is the standard set of Hamiltonian. You have this energy, you have the charging, you have a single mode, and then you have the electron-phonon interaction in the dot. Then you have the contact Hamiltonians, and then you have the tunneling Hamiltonians, and the total Hamiltonian is the sum of all these terms. So, of course, we do this Lang-Firsov transformation, where the energy levels of the quantum dot are they get changed to E minus lambda square h nu and so on. And this is a very famous transformation. And what I showed you, for example, is these Fock space levels where you have zero, single charge and double charge levels. Now you have copies of these levels happening because of the phonon subspace, right? Because you have n phonons. Each state has, characterized by not only the electronic states, but also the phonon numbers, right? So therefore you have this whole, these things repeating in copies, right? In the phonon space. Yeah, and then the formulation follows this standard master equation approach where you calculate these transition rates which come from the Fermi's golden rule, and then you have these overlap elements which actually give rise to some interesting features that include, the Frank-Condon effect and things like that. Okay? So this is a simple rate equation that you're solving between all these states. Now, from the rates, we can calculate the currents because currents are nothing but, rates times probability. Inflow minus outflow gives you the current in probability space, right? So we can calculate from the master equation the steady state probabilities. From that, you can calculate the electronic charge current, the electronic heat current, and the phonon heat current, right? So some of these recently published work is the fact that what we showed is that in the presence of phonons, when the phonons go out of equilibrium, you actually have a better performance when you have this n-type quantum dot rather than a p-type. N and p simply means in electrical engineering convention that if the energy level is below the chemical potential, it is like a p-type because whole conduction, because it's a field level. And if the energy level is above, it's called an empty level, and that's called electron. So it's electron or whole conduction. And then there is this negative U region, which is basically from the Lang-Firsov transformation, you could get a negative U. So one of the things we showed in this work is that basically you can also measure the non-equilibrium temperature of this dot. Because the phonons are going out of equilibrium, we have this weakly coupled bath, and you want to make the current zero, which we vary the temperature here and make the phonon heat current zero in this leg. And that gives us the temperature, because when the phonon heat current is zero, that means this and this are in the same temperature. It's just one way to calculate the temperature. And what we see is that the temperature of the molecule deviates as you couple the device strongly to the contacts. It also deviates with finite electron-phonon interaction parameter lambda. And so the sense of currents, you can always use the Kirchhoff laws. There is like, currents can flow out of the dot or into the dot, into the bath, outside the bath, and so on. So we can characterize two different phonon baths, which is the hot bath and the cold bath. And another work we pursue right now is that we can get a phonon heat current as a function of voltage. And that's a very strange phenomenon because it really signifies a Peltier effect from the phonon side. I hope those who do not have this know about Peltier effect. Peltier effect is that when you drive an electron current, you have cooling on one side and heating on the other, because electrons dump into the other side and this region gets cooled. And that's the opposite of the thermoelectric effect. It's called the Peltier effect. But that's an electronic effect. So you can also have a phonon Peltier effect where the phonon currents vary with voltage. And then we can see that this is a signature of the non-equilibrium phonons, because you have this phonon with the phonon number deviates from the equilibrium value. And then we can calculate the Peltier coefficient, and we can also find regions where this cooling can happen. So this is basically the phonon work. We also, so these are the applications I can think about. One is this power efficiency trade-off gets better. Next is non-equilibrium phonons can give rise to regions where the efficiency is optimized. Then we can also have a cooling effect from the hot bath, which is very strange. And we can also have a switching as the lambda is changed. The lambda is the electron-phonon interaction parameter, because you can switch on and off this phonon currents. So that's a very interesting effect here that we see. So I'd like to move into this information batteries now. Now that we just gave a flavor of the non-equilibrium bath, we'll talk about this, batteries. So what is a battery? The standard electrochemical cell simply, goes from an excited state to ground state, and then, a voltage develops between the two ends, right? So any battery works in such a way that you have, the chemical you're just transferring charge from one side to the other, so there is this chemical potential difference that is built up, right? So what really, so we'd like to quickly see that there is this energetic picture or the free energy picture. First is that, whenever you consider, it's like a chemical reaction, source injects electrons, then it sort of exits electrons. So you have this N1 plus N2, the number of electrons is conserved, the energy is conserved, but this entropy is not conserved. This is a standard second law, and the direction where this entropy is less than 0. Actually, this convention is minus delta S, because this is when you take away something, you have this negative sign. So basically, this is a standard second law of thermodynamics. Whenever this happens, you have a flow of electrons and things like that. Or the direction of the flow of electrons really depends on this term. Now, as I showed you, there is this whole idea of this non-equilibrium demons. What is a non-equilibrium demon? Firstly, an equilibrium demon is a reservoir or a phonon bath or something like that, where the temperature, it's maintained at a temperature. Whereas a non-equilibrium demon is basically a bath whose states are given by the Shannon entropy or the Boltzmann entropy. It's called K log W. So it can be in a different entropy rather than the maximized Gibbs distribution, right? So these are not science fiction items, because there are lots of cases. For example, the 3 talks by Dr. Jason Petta was talking about, double quantum dots interacting with nuclear spin bath, which is a very popular thing. We can also have spins strewed around in this dilute magnetic semiconductors and so on. So these are all baths that can go out of equilibrium, okay? So that's what I would focus on. So this is a generic situation where I have this source and drain contacts, current flows, but there is also an information source, which I will explain you at this point. So what is information? Information is basically, if you know the knowledge, if you have the knowledge about something, the information is 0. That's the Shannon information, right? That's what we use in digital communications. For example, if all spins are polarized or a car registration plate is 999, you sort of think it's very trivial. But if it's unpolarized, then the entropy is maximum. So that's the information content, right? So you can actually draw energy, you can actually make it function like a battery, simply because this free energy is the sum of, the difference of the change in energy and the change in information. So you can actually drive a current through this information source. So I would like to describe a setup where you can do it. It's quite a popular setup. You have spin polarized contacts. This is quite common in this area of spintronics, where you can have a magnetically polarized situation. So if the spins are, oppositely polarized, then there is no current through the device as you would expect, because this is upspin, it enters in, but it can't flow into a downspin contact if it's perfectly polarized. However, it can interact with this nuclear bath, which is sort of polarized, and then you can have a preferential motion from the left to right, because, for example, if this is all polarized up, then the downspins come in and become upspins and go out because of the spin flip processes. So therefore, you can actually drive a current through these transitions, which are basically horizontal transitions in Fock space. That's basically doesn't change the electron number, but flips the electron. So this spin flip, hyperfine spin flip, is it's quite a common thing, and it's sort of there in all systems. We solve this situation using this so-called self-consistent approach, where we calculate the probabilities, but based on this so-called, the nuclear rates, and then the nuclear spins also exert a magnetic field back on the electron. It's called the Overhauser field, and so all this is included in this situation where there is feedback effects. I'll get to that in a bit. So these are the set of equations, simple master equations. What is interesting here is that you have this information current that is simply flowing it's not something that flows, but it is sort of information is flowing from the path to the system, right? So we can calculate this quantity. So let me explain you how this information battery works. For example, if this bath is polarized in a particular way, the electron from here comes in, but it will flip because of the nuclear spin, and it will go away. So that's where the current starts to flow, and then this bath tends to develop a particular polarization. So one of the things that happen in the information batteries, you start with a fully polarized bath. Electron comes in, let's say from here, flips, goes, and then it becomes unpolarized. Once it becomes unpolarized, you cannot drive a current anymore. So it's a transient power source, right? Once it becomes unpolarized, this fellow comes, there's no current anymore. But if you polarize it in a particular way, you're actually drawing, energy from a non-equilibrium bath. This is the standard Charlie Bennett proposal on this Landauer limits and things like that. So basically, when you are fully polarized, the dimmon is happy, right? When it's unpolarized, the dimmon is tired, it cannot drive the current anymore because it has lost a lot of information. It's basically the NKT log 2. As you can see that the currents are transient, they sort of flow and they die down to zero, and the currents are there as long as information currents are there and things like that. So this is the set of plots that show the battery functionality. So there is this big connection with the Maxwell's demon, right? Because Maxwell's demon says there's this intelligent creature that sort of, divides, creates a temperature gradient, or in our case, we drive an electron flow from the left to the right? So this is the famous solution of the Maxwell's demon problem, which is Leo Szilard's very interesting title, on the decrease of entropy in a thermodynamic system by the intervention of intelligent beings. So it's a very famous paper. I think he has pretty much solved it all, Leo Szilard in 1929 or something. So the Landauer limit for computation is pretty much all there in this paper. So here's the moral of the story. So you can either, sort of drive a battery through this energy change or through the information. And that's what we sort of showed. And there are lots of experiments also on this hyperfine battery, and it's kind of, there all around. So, and then this all is connected with this whole, Landauer limit of erasure and things like that. So what we are doing essentially is we are erasing. So basically you're starting with a known state, right? And then you go into an unknown state. And the process of coming from an unknown state to a known state is the erasure. For example, you can record an entire symphony on a tape and erase it to all, in one direction. That's called erasure, right? And the erasure is what causes at least that much amount of energy should be expended. So there's this NKT log 2, which is the ultimate limit of computation, that I mean, even if you can do all processes adiabatically or reversibly, there is an irreversible thing due to the erasure. That's the Landauer limit of erasure. So anyway, so here is, we also showed that the information flow can also give rise to some better thermal machines like thermoelectric efficiencies and things like that. So of course, this larger than Carnot is only a transient phenomena, and that's possibly because we have not accounted for the information flow. It doesn't violate the Carnot theorem's spirit. So one more thing that I would like to introduce is this Pauli blockade situation, which was explained for the 3 lectures of Jason. So interestingly, we also solved this Pauli blockade problem where the singlet triplet levels in a double quantum dot can sort of basically this hyperfine splitting, the hyperfine interaction can cause a current to flow from Pauli blockade. This is a famous experimental feature where there is a hysteresis in the current versus magnetic field characteristics, which we are able to capture. And this is a very important thing because it is due to the Overhauser field. It is due to the feedback of the nuclear spins back into the electronic states. Yeah, yeah, yeah. Yes, the phonon part, again, I'm not sure how to connect with the information theoretic way of thinking. We probably don't need it. Yes, right, right. That's about it. Yeah, right. Yeah. 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 Yes, it's just in a device context, that's about it. You guys probably know it quite a lot. So, no, but the chemistry community. Yeah, right. Okay. Yeah, so now when you have a strongly coupled bath, you can actually have entanglement between the system and the bath. And in fact, in this setup, we can show that as a heat engine performs its operation, you can actually entangle these 2 species that were not entangled to begin with or cannot get entangled because there is no interaction between these 2. It's just that these both are talking to this dot through a J interaction with S1 dot S2 type of interaction. So again, here, of course, we'll have to move into this, there is this degenerate coherences, and we'll have to go into a slightly more advanced version of the master equation, and this is basically the density matrix master equation. And so, for example, there are these set of states that are sort of degenerate, and that's why we have to use this density matrix master equation. There is this virtual tunneling processes that comes out of this. So you can solve this bunch of master equations, you get a lot of complicated terms, and in the simple spin limit, you can actually relate it to precision. Because, for example, if the 2 leads are non-collinear, then you can see that you can sort of shoot into a superposition of up and down, and that's the degenerate states where you can sort of have this spin precision. That's one interpretation of this word. So then here you have the standard set of, Lindbladian. It looks Lindbladian, but I'm not sure how to connect them. But you can see that there is this term that sort of talks about the coherent evolution. And this sort of talks about the dissipation or a dissipator type of things. So one of these funny things we saw is that, of course, the current, it's a standard battery function. The current goes down in that battery. But what happens is that the concurrence builds up. Concurrence is one measure of entanglement between the 2 spins that I was talking about. And it's just, I don't understand this meaning of this particular quantity. It's just that for a tripartite system, people talk about concurrence. So we just calculated it, and it turns out that the concurrence does not develop at a particular voltage. It happens only below a voltage. So we see that we can actually switch on and off the concurrence based on the voltage. So you can have this 0.33 concurrence, and then suddenly it switches off when the voltage becomes equal to the interaction parameter and so on. So this is an interesting transition that we see, and we got a very simple energetic explanation about it. So I would like to sort of conclude that this whole topic of open quantum systems is what we electrical engineers do for a living, but of course, if you connect this standard flow with this out of equilibrium demons, it gives rise to very interesting possibilities, which I sort of hinted at this point. So one quick thing, that this whole quantum transport is a very popular area in our electrical engineering community, because devices got shorter and shorter. We got into this whole bottom-up viewpoint where you have quantum limit, and you cannot use the standard diffusion theories. So therefore, we have this whole formalism that sort of, the Keldysh formalism has been sort of developed to such an extent that it's kind of used by engineers quite often. So I'd like to conclude my talk. I'll thank you once again for giving me an opportunity to speak here. And yes, so the lead is, it's actually a collinear leads, but because this thing is coupled to the other two spins, it can have an arbitrary angle. So when you have, like this situation and the spin is pointing in some weird direction, you do have coherences, that's all.
Usually this master equation approach or this rate equation approach doesn't work very well when there is a degeneracy. I mean,
yes, that's why
so
we have that's why there is an extension of that approach, which is basically based on this. It's basically in the degenerate space. You can also do this. That's why you have these virtual tunneling processes that come in and so on and so forth.
Right.
It's a different thing. It's not the standard master equation on probabilities, but you are talking about density matrix now, where you have the off-diagonal terms too.
Right. I think that's clear, but I'm just wondering, because you said that the master equation or rate equation is valid when this broadening is much, much smaller than the energy sum. So now in this case, actually, because the energy gap is almost zero, the broadening,
is from the contacts.
Right. So any infinitesimal amount of broadening will break down that condition. So I'm just...
That's true.
Yeah.
That's a limitation.
Like what is kind of done in the electrical engineering community? Maybe you can mention what are the latest questions that people are interested in.
Yeah. So some of the important things we guys work on, we use this quantum transport to model a lot of upcoming devices. They're called the emerging and exploratory devices. That CMOS technology which drives your laptop is coming to an end because we are in the 14 nanometer node or something, and then beyond that, they have to look for alternate devices, right? So spintronics is one area which electrical engineers work on. In fact, there is this whole MRAM field, magnetic random access memories. In fact, spintronic MRAM is kind of already there in the market. There's Samsung working heavily on it. So these are the upcoming devices in the quantum regime. Also, there is this qubit and things like that, which is based on through the zero bias, conductance and things like that. So devices that way, a lot of options to work on. I think today Intel is the chips that are there in your lab. They're testing the 7 nanometer node also, but I don't know how. But that's it. That's as much as you can get.